And I'd like to move on to our next speaker, which is Professor Daniel Siegel from the Perimeter Institute. Dan, if you want to turn on your video, we don't see you yet. Perfect.
Hi there. Can you see my slides?
Yes. And
okay,
do you have
perfect.
the timer pinned as well?
I do have the timer pinned, yes.
Perfect. Thank you.
Okay, well, thank you so much, Manzi, and thanks to all the organizers for the opportunity to speak here. So in this talk, I'm going to focus on a rare class of core collapse events that we hypothesize give rise to a new type of transient that we call super-Kilonovae. These are presumably very rare events that might be detectable by Roman, and as we show in this recent paper indicated down here, Roman in its sort of blind supernova type 1a survey will be able to detect a handful of such events per year. These events might signal actually the birth of very heavy black holes in the so-called Pair-instability supernova mass gap. So it's pretty exciting to probe the fate of massive stars. So just to set the scene, essentially, as you may be aware, LIGO, Virgo, Kagra have just concluded their third observation run, finding quite a number of binary black hole systems in which the primary and or secondary black hole actually resides in this Pair-instability supernova mass gap between roughly 50 and 130 solar masses or so, in which, according to conventional stellar evolution theory, black hole remnants are not thought to be produced, as you can nicely see down here in this recent work by Renzo et al. Well, there have been a few ideas on how to potentially form black holes in this mass gap, and I've indicated a number of papers and ideas down here. And so here's another idea, which is, I would argue, fairly straightforward and actually a quite natural way of forming heavy black holes in this mass gap between 50 and 130 solar masses. And so basically the idea is that very heavy progenitors residing above the mass gap at the onset of core collapse, as indicated by these blue dots up here, if those are rapidly rotating stars, upon collapse, they will form a black hole surrounded by an accretion disk, as you can see down here. And this accretion process in these, in such a sort of very massive super collapsar, if you want, gives rise to massive winds from the accretion disk that causes mass loss to the system. And so eventually the final black hole, after completion of all the accretion of the progenitor, will actually lose, as we show, up to tens of solar masses, and eventually then reside in this Pair-instability supernova mass gap. Now, in concrete terms, we use models from Matthew Renzo, which, as you can see above the mass gap, these massive progenitors are very compact stars. So this is a mass radius diagram where you can see that most of the mass really sits somewhere between 10 to the 9, 10 to 10 centimeters. So they are very similar to some of the Wolf-Rayet stars, which are the progenitors of ordinary collapsars below the Pair-instability supernova mass gap. And so we endow these models with rotation profiles just to parameterize in a parameterized way to essentially parameterize our essentially the uncertainties in rotation profiles of these massive stars. Essentially, we start with a specific angular momentum profile of this type, essentially broken power law, if you want, a power law up to some break radius that is sort of motivated by the stellar structure. And then some sort of more rapidly rotating envelope that rotates at some fraction fk of the local Keplerian specific angular momentum. And so with these two free parameters of the rotation profile that we endow these stars with, we can scan the parameter space and evaluate, according to our model, what the final black hole mass would be. And as you can see for this particular model here, which is one of these, corresponds to one of these blue dots up here, but it's very similar for all the other ones as well, you can nicely sort of populate the entire mass gap between something like 60 to 130 solar masses, as you can see color-coded down here as a function of these rotation law parameters. Also, to guide the eye, here are some red contours that indicate one of these particular very heavy black hole, binary black hole merger events that LIGO has detected last year. Now, coming to the transient, essentially, so these winds from the accretion disk as they move into the interstellar medium will produce a transient that is very similar to kilonovae from neutron star mergers. So you can argue this is a sort of scaled up version of very red transients similar to neutron star mergers, and hence the name Super-Kilonovae. And so the composition here is quite important in setting the colors and some other properties of the transient. And so the composition really reflects the accretion process, the accretion history of these progenitors. As I mentioned, these are very compact stars, so they give rise to very high accretion rates initially. And at those high accretion rates, the accretion flow will typically neutronize, so there will be some neutron excess. And as Jenny nicely explained in her talk, in such conditions, the R process can proceed. And so indeed, what we find here is that in the early stages of this collapsar accretion process, the flow nicely neutronizes, gives rise to R process nucleosynthesis, produces lanthanides that boosts the opacity, as Jenny explained, and drives the transient very red. So there can be various accretion and corresponding nucleosynthesis regimes, all of which has been explored previously already. So here on the left, you can see a representative model from these very massive collapsars that we are looking at here. And as you can see, there's so for the first 20 to 30 solar masses of ejecta, the accretion rate stays in a fairly high regime where the flow is sufficiently neutron-rich to undergo a full R process and produce lanthanides. So this is where essentially these high opacities are generated. Then typically there's also at somewhat lower accretion rates a regime where the flow is not neutron-rich enough to undergo a full R process, but still light R process elements with lower, bluer sort of opacity will be produced. And finally, as we get to the sort of outer envelopes, the accretion rates drop below a critical so-called ignition rate, where the neutron richness is not sufficient to produce an R process, and so but still a sizable amount of nickel 56 can be synthesized. And so if we scan over the parameter space of these models, scanning over the different parameters of the rotation law, I've shown a few examples down here. We typically find ejecta masses of anywhere in between 10 to 60 solar masses, which means that the final black hole masses will be anywhere, as I mentioned, between 60 and 130 solar masses. The total R process material might be anywhere in between 1 and 20 solar masses, a lot of R process ejecta. And the amount of nickel 56 being produced may be anywhere in between 5% and maybe a solar mass. And the typical lanthanide mass fractions, just to point this out in terms of opacity, so the lanthanide mass fractions we typically find are anywhere in between 10 to the minus 4 and a few in 10 to the minus 2. So there's significant lanthanides in there, and that makes these transients very red, as you can see here. So essentially, scanning over the parameter space and progenitor models, we find more or less 5 representative super-kilonovae light curve morphologies shown here on the left, labeled as A to E, which resemble some volumetric light curves of other types of supernovae, in particular these type 2P supernovae with these plateau-shaped features here in red and green, which are the reddest transients we find here. So this morphology is really due to the fact that we have both a nickel 56 plus R process powered transient, and you can be anywhere on this gray scale between a nickel 56 dominated versus R process dominated transient. So timescales typically of tens of days. Very red colors, so a scaled up version of neutron star mergers, hence super-kilonovae, and the spectra are very distinct from other transients. As you can see here on the right, they all have broad line features at peak light, owing to the fast ejector speeds of typically something like 10% the speed of light, which is the typical speed with which these ejecta come out from the accretion disk around the black hole. Now, what does this mean in terms of detection prospects and Roman? So there's two ways to go after these kilonovae, these super-kilonovae, either via targeted follow-up of very bright long GRB events in the infrared with Roman or JWST. So we also hypothesize that long and very energetic GRBs may be produced in this accretion process. Or the other option is to go for blind searches with optical and infrared surveys such as Rubin or especially Roman. And you can see some numbers here in the table. So essentially an optical survey like Rubin would be most sensitive to nickel 56 ejecta and light R process material mostly, while Roman will be very sensitive to the sort of red component, to nantonide rich ejecta material. And so assuming a scaled up beaming corrected GRB rate to above the upper mass gap using a salpeter IMF, assuming 10 square degree Roman type 1a survey with these filters and going to roughly 27th magnitude, we find that a handful of events, at least for the reddest morphologies, can be observed per year with Roman. There is uncertainties, obviously, that I don't have time to go into. The detection prospects obviously depend on the survey strategy. So this is a figure that Ashley Villa kindly compiled, showing the depth versus cadence. So essentially the takeaway here is that we need a survey with cadence of 1 to 2 months for a planned depth of something like 26 to 27th magnitude if we want to detect at least a couple of these super-kilonovae per year. Finally, I just wanted to point out in 2 seconds that these are also multi-messenger events. We also do expect gravitational waves actually from these events, but those are low frequency gravitational waves events from non-axis symmetry, from instabilities, non-axis symmetric instabilities in the accretion disk. And so we need third generation gravitational wave observatories. So if Roman is around long enough, we might actually, it might overlap with Einstein Telescope and Cosmic Explorer, and we could even see these events both in gravitational waves and as red transients. And I'll just leave you here with the conclusions since time is up, and I'm happy to take any questions. Thank you.
Thank you, Dan. Questions? I don't see anything in Slack or Zoom. Dan, you should know I take your papers very seriously. I have a graduate student losing a lot of sleep right now to test your hypothesis.
Oh, that's nice. I'm glad to hear that.
But if anybody would like to unmute and ask a question, you're very welcome to as well. So I don't see anything in Slack. Let me just.
I'm also happy to follow up over Slack if people have questions later on.
Okay.
You have a question from Igor. He has his hand up.
Oh, Igor, please go ahead.
Thank you. Yeah, I was wondering why you think we don't yet have candidates for this type of sources. Is it more likely that we have a lot already in the bucket, we just didn't recognize them, or do we indeed need Rubin and Roman for them to be discovered?
Yeah, that's a great question. So in principle, there could be already candidates. So I was talking about very energetic long GRBs. So in principle, maybe there might be a subclass of GRBs that could potentially represent such events. But in general, they are fairly rare. So they are suppressed by the salpeter IMF going to these very high masses of stars. So the rates are very low. And so a very comprehensive survey over a long time will be needed to really identify some events. So I think it's really the rarity of these events that makes them hard to find.
Thank you very much.
Mm-hmm.
All right. Any other questions? Okay. Please feel free to put them on Slack.